Now that you're well rested, we are now ready to proceed to part 2. Now that we're done with model development, let us go to the second step of the quantitative process, which is data preparation. Data preparation is not a trivial step, meaning it is an important step because it requires time to do so, and collecting data may involve errors. In the preceding example, we only have one decision variable and two constraints. But what if we have a model with 50 decision variables and 25 constraints and over 1,300 data elements? The possibility of making a mistake would then be higher. In this case, we would need a fairly large database to support the mathematical model, and information systems specialists may have to be hired in order to solve the problem. Let us now move on to the third process, which is the modal solution. In the modal solution, we may have many alternatives to choose from. An analyst will have to identify which among the alternatives provides the best output for the model. For example, which among the alternatives can help the company achieve maximum profits? The best output is considered as the optimal solution. An alternative that does not satisfy all the constraints is called infeasible, while an alternative that satisfies all the constraints is called feasible. To make this clearer, let us illustrate. Suppose that we have 5 alternatives. So we have alternative 1, alternative 2, 3, 4, and 5. Now assume that alternative 2 and 3 do not meet all the constraints, so they are considered as infeasible. So any alternative that is considered as infeasible needs to be rejected. Alternatives 1, 4, and 5 assume that they meet all the constraints, so they are considered as feasible. And these will only be the 3 alternatives that we are going to consider in making a decision. Now assume that alternative 1 will result in a profit of 100,000 pesos. Alternative 4 will earn you a profit of 200,000 pesos. And alternative 5 will earn you a profit of 300,000 pesos. So alternative 5 actually maximizes the profit. So we are going to choose, of course, alternative 5. And alternative 5 is what we call the optimal solution. So to recap, for the 5 alternatives, alternatives 2 and 3 are considered as infeasible because they don't meet all the constraints. Alternatives 1, 4, and 5 are considered as feasible because they meet all the constraints. However, from alternatives 1, 4, and 5, we are going to pick alternative 5 because it allows the company to achieve the maximum profit. And alternative 5 is the optimal solution. One procedure that might be used in the modal solution step involves a trial and error approach where the model is used to test and evaluate various decision alternatives. In this process, we just assume or plug in figures to represent X and use that to compute for the various projected profit and total hours of production. Based on the previous example given, the constraints are 5x should be less than or equal to 40, and x should be greater than or equal to 0. Now, if you're going to look at this table, the last two decision alternatives do not meet the first constraint because the total hours of production, 50 and 60, are greater than 40. Therefore, if you're going to ask, is it a feasible solution? The answer is no, because they are infeasible. Therefore, we can only choose from alternative x is equal to 0 until x is equal to 8. The trial and error approach would mean testing and evaluating the model under various production quantities or values of x. Through this process of evaluating selected decision alternatives, a decision maker can identify a good and possibly the best feasible solution to the problem. This solution would then be the recommended decision for the problem, which is obviously x is equal to 8 because it has the highest projected profit of $80. Although the trial and error solution process is often acceptable and can provide valuable information for the manager, it has the drawbacks of not necessarily providing the best solution and of being inefficient in terms of requiring numerous calculations if many decision alternatives are tried. Thus, quantitative analysts have developed special solution procedures for many models that are much more efficient than the trial and error approach. Throughout this text, you will be introduced to solution procedures that are applicable to the specific mathematical models that will be formulated. Some relatively small models or problems can be solved by hand computations, but most practical applications require the use of a computer. Examples of software that can help solve complex mathematical models are Microsoft Excel and the Management Scientist software, which is developed by the textbook authors. Although we will solve some problems later on using Excel, you will be acquainted with the advanced intricacies of Excel calculations in your third year. Once we would have already decided on a model, that model needs to be tested and validated. If it is deemed to generate expected solutions, then we can apply it on the actual full-scale problem. However, if testing the model reveals potential shortcomings and errors, then it is necessary to collect more accurate inputs and modify the model so that it can resemble the actual problem after such modifications. The last step of the quantitative analysis process is the report generation. The results of the model must be indicated therein in a managerial report, which should be understandable to the one who is making the decision. The report should include what is the recommended decision and other pertinent information about the results that may be helpful to the decision maker, such as sensitivity or what-if analysis. For example, what would happen if there are changes to any of the decision variables or uncontrollable inputs? How would such variations affect the recommended decision? It is then important to successfully implement the model results. The manager is ultimately responsible for integrating the quantitative solution with qualitative considerations so that he could make the best possible solution. After he makes a decision, his job is not yet done. He should continue to oversee the implementation and follow-up evaluation of the decision. Sometimes, it may require the management scientist to refine or expand the model depending on the request or additional needs and requirements of the manager or decision maker. Let us now look at other models, particularly models of cost, revenue, and profit, and other management science techniques. As business and accountancy students, it is important for us to analyze costs and revenues since the goal of a business is to generate profits. Moreover, financial and production planning, sales quotas, and other areas of decision making can benefit from cost, revenue, and profit models. Let us first look at costs. Total cost is usually defined as a sum of fixed costs and variable costs. Fixed cost is a cost that remains the same regardless of the units being produced. An example of this is electrical cost. If you produce 1 unit compared to producing 10,000 units, you still have to pay the same amount of electricity. On the other hand, variable cost is a cost that depends and varies with the production volume. An example of this is direct materials. Assume that you are in the business of printing books that consist of 100 pages each. If you print one book, you only spend for 100 pieces of paper. However, if you print 100 books, then you have to spend for 10,000 pieces of paper. Let us now take a look at this example featuring Nolin Plastics. Nolin Plastics produces a line of cell phone covers. Nolin's best-selling cover is its Viper Modal, a slim but very durable black and gray plastic cover. Several products are produced on the same manufacturing line, and a setup cost is incurred each time a changeover is made for a new product. Suppose that the setup cost for the Viper is $3,000. This setup cost is a fixed cost that is incurred regardless of the number of units eventually produced. In addition, suppose that the variable labor and material costs are $2 for each unit produced and that each Viper cover sells for $5. So for our requirements, we need to, number one, construct the cost volume model. Number two, identify the marginal cost. Number three, the marginal revenue. Number four, construct the total profit equation. Number five, the break-even point in units and in dollar sales. And in addition, we should answer the question, how much would be the profit or loss if 500 pieces of Viper is sold? And lastly, how about if 2,000 pieces of Viper is sold? Before we start answering the requirements, let us first take a look at some of the definitions of the terms being asked in the requirements. First, we have marginal cost. Marginal cost is defined as the rate of change of the total cost with respect to production volume. That is, it is the cost increase associated with a 1 unit increase in the production volume. This, therefore, includes only variable cost and not fixed cost. Next, we have marginal revenue. It is defined as the rate of change of total revenue with respect to sales volume. That is, it is the increase in total revenue resulting from a 1 unit increase in sales volume. Total profit, denoted PX, is total revenue minus total cost. Break-even point in units is the volume that results in total revenue equaling total cost, which provides zero profit. And break-even point in dollar or peso sales is the dollar or peso sales that results in total revenue equaling total cost, providing zero profit. Let us now answer the 7 requirements. First, we need to construct the cost volume model. Or in other words, we want to construct the equation that would help us find the total cost. We know that total cost is the sum of fixed cost and variable cost. So let it be CX is equal to fixed cost of $3,000 plus the variable labor and material cost, which is $2. And then we multiply that by X because it is $2 for each unit produced. The second requirement is to identify what is the marginal cost. In the definition earlier, we know that marginal cost only includes the variable cost and not fixed cost. Therefore, the marginal cost is 2. For the third requirement, we need to identify the marginal revenue. It states here that each Viper cover sells for $5. Therefore, the marginal revenue is 5. The fourth requirement is to find out the total profit equation. So that would be PX is equal to, so to find profit, that would be the total revenue minus total cost. Or in other words, RX minus CX. Our marginal revenue is 5. So 5 times the number of units minus, we just substitute it with our answer to the first requirement. So minus 3,000 plus 2x. So to recap, for the first 4 requirements, the cost volume model is Cx is equal to 3,000 plus 2x. The marginal cost is 2. The marginal revenue is 5. And the total profit equation is Px is equal to 5x minus 3,000 plus 2x. Let us write down again the total profit equation, which is Px is equal to 5x minus 3,000 plus 2x, because that will help us answer the remaining 3 requirements. So for the fifth requirement, we are tasked to find the break-even point in units and in dollar sales. So we know that break-even point is the point wherein the profit would be 0. So let us substitute the equation. If Px would be 0, so 0 is equal to 5x minus 3,000 plus 2x. So that would be 5x minus 3,000 minus 2x. Move 3,000 to the left side. So we have 3,000 is equal to 5x minus 2x. 3,000 is equal to 3x. Therefore, x is equal to 1,000. So this would be the break-even point in units. If you're able to sell 1,000 units, you would not have a profit, nor would you have a loss. Then we need to compute what would be the break-even point in dollar sales. So all we have to do is to multiply the break-even point in units, which is 1,000 units, multiply it by 5, which is the selling price per Viper cover. So that would be 1,000 units times 5. Break-even point in dollar sales would be 5,000. Now for the last 2 requirements. But before that, let us write down the total profit equation, which is Px is equal to 5x minus 3,000 plus 2x. And then the break-even point in units, which we have solved in the previous slide, is 1,000 units. If the break-even point is 1,000 units, then if we sell less than 1,000 units, then we would incur a loss. The only time we can generate a profit is if we're able to sell more than the break-even point of 1,000 units. So let us now answer requirement number 6. How much would be the profit or loss if 500 pieces of Viper is sold? Now, since in this assumption, we will only sell 500 pieces of Viper, which is less than the 1,000 units of break-even point, then it is obvious that we would generate a loss. So to compute what is the amount of loss, all we have to do is to substitute x for 500. So P 500 is equal to 5 times 500 minus 3,000 plus 2 times 500. And that would be 2,500 minus 4,000, which is negative 1,500, or loss of 1,500. Now, number 7, how about if 2,000 pieces of Viper is sold? Now, since 2,000 pieces is greater than 1,000 units, which is the break-even point, then obviously we would generate a profit. So let us compute how much is it. So substitute x for 2,000. So P 2,000 is equal to 5 times 2,000 minus 3,000 plus 2 times 2,000. This would be 10,000 minus 7,000, which is positive 3,000. And that would be profit because it's positive. So for number 6, you would have a loss of 1,500 if you sell only 500 pieces of Viper. And for number 7, if you're able to sell 2,000 pieces of Viper, then you would have a $3,000 profit. This slide shows us the break-even analysis graph for Nolin Plastics. This is the total revenue line, and this is the total cost line. Fixed cost is set at 3,000. The point where the total revenue and total cost line intersect is called your break-even point, which is 1,000 units. Again, as mentioned in the previous slide, if we sell less than 1,000, then that would be a loss. However, if we sell more than 1,000 units, then you would generate profits. For your individual graded assignment, please answer problems 10 and 12 from Chapter 1 of your required textbook. You may submit your answers through our Canvas platform. The following are the other management science techniques that can be used to help make better decisions. Let us look at the definition of these techniques in the subsequent slides. First is linear programming, which is a problem-solving technique in order to maximize or minimize a linear objective function which is subject to certain constraints. Next, we have integer linear programming. It is a subset of linear programming. It has all the characteristics of linear programming except that all numerical values have to be in integers or whole numbers. So, for example, upon performing the technique, you found that the result is, let's say, 2.9, that solution is incorrect since 2.9 is not an integer. Third, we have distribution and network models. These are special procedures related to transportation and assignment problems. Next, we have nonlinear programming, which, like linear programming, deals with maximization or minimization objectives. The difference is that while linear programming deals with linear functions, nonlinear programming deals with parameters or requirements that do not have a linear relationship. Next, we have PERT-CPM. PERT-CPM is a scheduling technique that helps managers plan, schedule, and control projects. It looks for the critical path and determines how long it will take to complete an entire project. Then, we have inventory models, which are used to determine how much inventory should be ordered every time an order is booked in order to incur the lowest inventory ordering and holding cost. Next, we have waiting line or queuing models. These are constructed so that queue lengths and waiting time can be predicted. This is important, especially when providing a service, because if the waiting time is too long, it can detrimentally affect customer satisfaction. Then we have simulation. Simulation is a technique using a computer program designed to predict the behavior or outcome of a real-world or physical system. Then we have decision analysis. Decision analysis uses the Bayes theorem and decision trees to determine the best strategies when dealing with uncertain future events. Then, we have forecasting methods. These are techniques used to forecast what would be the future outcomes of a business operation. Goal programming is an extension of linear programming which deals with handling multiple, normally conflicting objective measures. Then, we have analytical hierarchy process, which is a structured technique used to organize and analyze complex decisions based on mathematics and psychology, as it analyzes not only objective factors, but also subjective factors when making a decision. Then, we have the Markov process models. It is a stochastic model which deals with studying the evolution of systems over repeated trials or sequence of observation. An example is to determine whether a current machine will function or break down in the future. And among the methods used most frequently in the real world are these four: linear programming, integer programming, network models, and simulation. Among these four methods, we will tackle linear programming and network models in AC 1103. Integer programming will not be discussed due to time constraint, but it doesn't really matter since it utilizes the same procedure as linear programming. Simulation will be covered in your third year. And that is the end of Unit 1. If you have any questions, you can post in our Facebook groups or send me a PM. Your assignment is to answer problems 10 and 12 in Chapter 1. The deadline is on September 3, 2020 by 10 p.m. It will be available to answer starting August 26, 8 a.m. Please follow the instructions in submitting your assignment. Also, please don't forget your academic obligations for AC 1103, such as answering your post-test, submitting your assignments, and participating in the discussion boards on or before the deadline set in Canvas. Have a nice day!